Fortran is a strongly typed language, meaning that all of the different types of things we're going to look at will have various categories that they fit into. And in this video, I want to take a short look at the categories that are going to be important to us. I will not make you suffer through my bad typing, so I'll just present these things as we go along. Optionally, you can say program and then give it a name. Letters and numerals, don't get too fancy with the program name. If you have a program statement, instead of just saying end, which you could still do on many compilers, we'll say end program. The statement implicit none, for now, I'm just going to treat that as something that I should put in my program. We'll talk about why that's there in a little bit more detail later. Suppose that I want to have two variables of type integer. The modern way that we declare our variables is to say the type of the variable, which is integer in this case, two colons, followed by a list of names of variables that we want to have in our program. Many people will tell you that you don't need those two colons. Strictly speaking, that's right. The program will still compile and work without them, but you should put them in anyway, because later on we'll use these as delimiters when we put various additional specifications on the data type, on the integer here. So just get used to it. Say integer, colon, colon, list of things separated by commas. To put a number into one of these variables, I'll say that I equals 3 and j equals 4. And for the first experiment that we'll do involving variables, I'm going to add these things together. I'm going to subtract them. I'm going to multiply them. And in the case of the quotients, I'm going to look at I over j and j over I. And remember, I is 3, j is 4. I've already compiled this, so I'll just run it. Here in Silverfrost, we see the usual banner that tells us that this is the personal edition. Let's see, 3 plus 4 is 7. 3 minus 4 is -1. 3 times 4 is 12. That all seems to be as it should be, but I divided by j is 0, and j divided by I is 1. That's because these are integer variables that we're taking on here. Since I and j are both integers, I over j is interpreted as an integer value, and so is j over I. So if you do the division in integer and then throw away the remainder, which is what it's done here, you'll get a 0 or a 1. Obviously, if you're wanting to do things with floating point numbers, integers are not going to get the job done for you. Also, I've opened up Simply Fortran and I've copied and pasted from the original window into this new one. Also, I've made the fonts bigger so that it's easier to read. I've already saved the file. I've already compiled it. So here, I'll just run it. And we see that we get 7, -1, 12, and 0, 1, just as we did in the first version. To look at a floating point version of this, we're now going to have two variables named u and v. Their data type is not integer though, but real. There's another floating point type, but we'll talk about that in a little bit. So I'm going to have u and v real variables. I'm going to set u equal to 3, v equal to 4, and then I'm going to do the same thing that we did with the integer version. I'm going to print out the sum, difference, product, and quotient both ways, u over v and v over u, and see how the results differ from those involving the integer calculations. And the sum is 7, but 7 point and some zeros. The difference is -1 point and some zeros. The product is 12 with decimal places after the decimal point. The quotient one way is 0.75, which is 3/4, and 1.33333, which is 4 over 3, to the specified number of decimal places. Likewise, I can copy and paste the program that I was using with Silverfrost, put it into the excuse me, put it into the Force compiler window. I've already compiled the program, so I just have to run it, launch project, and I get 7, -1, 12, 0.75, and 1 point, a bunch of 3s, and a 7. There's two things to note here. Number one, materially, these are the same results the other compiler gave us. But secondly, it's printing more zeros in those first 3 lines and in the 0.75. Also, it's printing more 3s out in the 1.3 number. But possibly most interesting of all, it rounded it up to a 7 at the end. So the number of decimal places being displayed is not the same between the two windowing compiler systems. And there's something funny going on with that 7 at the end of the last number. When we speak of how the computer stores these numbers in literal terms, we will come to understand where the 7 is coming from. The short answer for right now is it's nothing to be concerned about. Early on in the history of Fortran, it was quickly revealed that the accuracy in real variables was not up to the task for many applications. As a result, a second type of floating point variable was introduced called double precision. And as you might imagine, usually what that amounts to is twice as many binary bits are devoted to a double precision variable as opposed to a real. The distinction introduced several subtle problems, which we will talk about later. But for now, I just want to declare variables u and v to be double precision. U will be 3, v will be 4, and we'll print out the sum, difference, product, and quotient both ways, just as we've done before. I've already saved the file. I will rebuild my project and then start the run. At some point, I'm going to start using other compilers than Silverfrost for my demonstration purposes because of the annoying banner. But for the moment, 7, -1, 12, 0.75, 1, and a bunch of 3s. You'll notice that the number of digits printed out is considerably larger than it was for the real. That's because more bits in the actual binary representation actually have meaning to them. Meanwhile, over in Simply Fortran, I've already changed my file. I have already compiled it. So when we run it, we get this for our results. And you'll see that it's basically the same as in the other one, except I may have a few more threes there printed out. It seems as though the exact number of digits that one of these programs is going to print out may depend on the defaults of whoever put the compiler package together in the first place. And this turns out to be true. We will find ways to adjust the output to make it look as we like. More recently, not only are there real floating point data types and double precision floating point data types, but some compilers now also support a quadruple precision data type, which has 4 times as much storage as an ordinary real and twice as much storage as an ordinary double precision. After a while, people began to wise up, though. In 10 years, when 256-bit floating point numbers are directly supported on the hardware, they thought to themselves, are we going to make up yet another name, or are we going to do something clever? So they introduced the idea of real kind. If I say real, open parentheses, kind equals 2, close parentheses, and then double colon u comma v. This tells the compiler that I want to have floating point variables that have twice as much storage associated with them as the usual real variable does. So this will be double precision. It compiles correctly. And when I run it, I see that I get the same results as I do when I actually literally said double precision U and V. So later down the road, when higher accuracy floating point numbers are directly supported on the hardware, the compiler can be tweaked a little bit by adding a little bit more code to it. And at some time, if not the present, kind equal 4 and kind equal 8 and so on will be directly supported. I'm not sure if this compiler supports these yet or not. So let's do an experiment. Kind equal 4. Build. It didn't complain any. Well, it looks like kind equal 4 doesn't really do anything other than what kind equal 2 did. So it looks like there's no provision for that here right now. Let's try that on Silver Frost. I'll change the kind to 4. It did not like that. The kind number is not supported. Meanwhile, over on Linux, I was reading the manual page, and there's an inconsistency between compilers as to what kind equals means exactly. On this version of G-Fortran, apparently kind equals 16 is what you have to try to get twice as much storage as a double precision number. But 16 didn't work on the other compilers that I tried. So this is sort of an idiosyncratic thing. But anyway, real kind equals 16, U and V, U is 3, V is 4. Print out the sum, difference, product, and both quotients. End of program. So I compile that here and then run it. And I'm getting twice as much digits as I was getting in the other compilers, it makes it a little bit easier to look at. Quadruple precision, even when it's supported by the compiler, typically is not supported in hardware. A real variable, or real of kind 1, as we might say now, typically has 32 bits of storage associated with it. A double precision typically has 64 bits. So since we have kind of, sort of 64-bit processors now, there's a direct hardware correspondence to bits in the hardware and double precision numbers. But if you double that, you would have 128 bits. There are no, as far as I know, processors in the mainstream that are 128 bits. This means that in software, if you want to use this quadruple precision, there's nothing parabolic about this. The hardware doesn't support the effort directly. You're going to have to do your double precision in software, which means you take a very bad speed hit on it. If you're doing some relatively simple short calculation, that won't matter in the least to you. If you're doing something complicated and CPU intensive, it will. It'll cause your program to run much more slowly than you might have thought. This has been a very short introduction to the basic sorts of data types that are going to be useful to us. In the next computer programming lecture, we're going to talk about some simple actual calculations. And then from there, we should have enough material in order to start solving some simple mathematical problems. I hope everyone's having a good day, and I'll talk to you again later.